Hello and welcome to the June edition of our webinar series, 60 Minutes. My name is John Kowalski. I'm part of the marketing team here at Bitgardner, and I'd like to welcome you. Can't believe it's June already. Time's just flying by. Today's presenter is Mr. Andreas Stummer. He's managing director of our VMA-Getzmann line for the US and Canada. And today he's talking about media milling deep dive. It's half of our dispersion series. Following the presentation, time permitting, we'll answer any questions you have. If you do have questions along the way, please log them in the chat box. It should be in the bottom right-hand corner of your screen. We'll get to them. If we do run out of time, we'll follow up with you directly. Either Andy or someone on his team will contact you to get your question answered. Also, we are recording this, so immediately following the presentation, and after we move on and close out this meeting, you'll receive an automated marketing link, marketing email with the link to this recording. So feel free to pass it to colleagues, check it out later in the week, next week. And if at any time you do have questions, you can always just hit reply to any of those marketing emails you get, and it'll be routed to the marketing team, and we'll get it to the right person. So with that, Andy, how you doing today? Welcome. Thanks for sharing your expertise with us today.
Hey, hello, John, and hello, everybody. Welcome to our presentation today. Appreciate everybody coming online. So actually, this is the second part of our dispersing and milling seminar series. And today we're actually going to do a close-up. We dive into the media milling component of the dispersion process. If you haven't had a chance to view or listen to the first part, as John mentioned, we have those online, and you can review the recording if you want to get up to speed. All right, with that, so we'll dive right in. First, we're going to do a little introduction about the company and the relationship that VMA-Getzmann has with BIC. Then we're going to talk about the dispersion process, just a quick review. And we're going to go right into the media milling component, and then we'll close it out with some review of different types of equipment that are used in the milling process. And then we talk also about some of the QC capabilities that allows you to track some of the results and the performance during the milling process, and then also a couple slides about the laboratory capabilities that we have here in the US at our sister company, BIC USA in Wallingford. They make the additives, and then also the lab capabilities at VMA-Getzmann in Germany. So as you can already see here, just on the bottom of that slide, we basically offer all the different solutions from laboratory scale to pilot all the way up to manufacturing. And of course, most of you know, or those of you that don't, all of the equipment, the dispermats that we offer have a modularity approach. That means that you can use them for dispersing, which is the first part of the process, and then also use them as media mills. So you see that on the picture, some of them are fitted as dissolvers with the cowls blade, and then you see other ones that actually have the basket mill attached on the same units. So that means that you can actually make that changeover yourself and turn a dissolver into a milling system very quickly. You can do that actually in under 5 minutes. You turn the dissolver into a media mill, which is a really nice feature. Just a quick overview of VMA-Getzmann. So these are the family-owned business, the manufacturer of the dispermats. The company was founded by that beautiful couple. You see a picture there on the top right, in about a little over 50 years ago in Germany. About 30 miles east of Cologne is where they are headquartered, in a little town called Reichshof, Germany. The company is still in family hands. It's run by the two sons, Christian and Martin Getzmann. And here at BIC, we have had the exclusive distribution rights for North America, specifically US and Canada. In Mexico, we actually have a distributor that resells the VMA-Getzmann products. But here in the US and Canada, BIC is fully responsible for the distribution of this beautiful line of products since 1988, actually. And it all started when, the former general manager here in the US actually brought some of the disperments over to use them in the lab space at BIC. And when customers came in to do lab tours, they saw these dissolvers and they were wondering how to acquire them here in the US. And that's when we made a decision to actually integrate them into the BIC Gardner product portfolio. And they became a staple of our product line ever since. So the company is growing rapidly. We have over 100 employees at VMA, and the company is known to make really high quality dispersing machines, bead mills, basket mills for the lab pilot as well as the production space. And then on the bottom right, you can see the very first dispermat was actually introduced 51 years ago, and it was the very first dispermat. It's a small laboratory scale unit. It's called the LC, and we have actually some customers that are still using the original designed dispermat. So there's unbelievable motor technology, but they only were actually replaced the control panel or the little control unit. You can see on the left side of the unit. But these motors are brushless step motors. So the shaft actually goes right into the motor. There are no belts or anything of that nature that require maintenance. So these are brushless step motors, extremely quiet and have hardly any vibration. So this product line is actually available in about 100 countries worldwide. And 40% of everything that VMA builds is custom. So there are a lot of new end-use markets that require specialties in terms of different types of materials, like a DLC coating, for example, or even gold-plated parts for some applications are required. So VMA is very flexible in that to make custom machinery. And then I mentioned that earlier, we also have very nice dispersion labs here in the US as well as in Germany. The picture right there is the facility of VMA-Getzmann in Reichshof, and they just added on another floor. And in the middle of the picture, you can see the big building. So they added a second floor for just design capability, and also that a building in the rear was added on for more production space. So really beautiful facility. About the dispersion process, let's dive right in. So why are we actually dispersing and milling? So it's really important because for a number of reasons. So we want to achieve better wetting of our additives that we are putting in and components. And then we want to break up these invisible binding forces. These are like electromagnetic forces that hold these particles or pigment particles together. And basically all we want to do is break up these binding forces. We don't want to destroy really any particles, we just want to really just break up these binding forces, then turn these larger clusters of particles, these agglomerates, want to turn them into aggregates. And then in the milling process, we want to turn these aggregates back down to the primary particle size. And we achieve this just through basically shear forces. And that will give us better product performance. So we can see improved color strength. Usually gloss is another component that's improved by doing good dispersing, overall appearance, but mainly our pigment efficiency goes way up, because we need to use less pigments now, because we're able to break them up and basically reduce the amount of pigments that we need to put into our formulas. That means we save money on raw material costs, And then we, of course, will get much better product consistency. Our formulations will improve. And if we do a good job, we should see consistent particle size distribution. And we should also get much better upscale results if we move that to pilot or production. Okay, if we don't do a good job dispersing, we should have some issues, right? So we have maybe a color shift, the poor stability of our mill base. We could see flocculation of pigments, which is actually usually resolved with using the right type of additives, where our sister company, Big USA, can support with that. Sagging, leveling, settling, or reduce gloss level and separation are some of the other problems that occur if we don't do a good job dispersing and milling. Here is a great example of why we need to mill. So on the left, you can see a product that was just pre-dispersed by using a cowl's blade. When we continued the process and we started the media milling, you can now see the product looks much better. It's basically a Hagman grind gauge, and we're able to just really visually see a difference between the two. So it's imperative that we don't stop just using a blade, that we actually use a media mill if we want to have a much better looking product. So here are some critical points. So stability. So obviously pigments require strong color fastness to reduce fading over time is one of the big benefits. Brightness, usually the brighter, the better the color. And then as a rule of thumb, pigment size plays a big role. So the smaller the pigment, we get some improvements to our product. So transparency, better color. And then, as I mentioned earlier, we save money by using less pigment in our formulation. And then another important point is viscosity. So usually we try to keep the viscosity on the lower end for improved particle size distribution, but mainly for processing of the material. So if you have something really thick and pasty, it's very difficult to work with that because it's hard to pump it through the mill. Even if you use a horizontal media mill, there is a plunger system, but it makes it more challenging to get the material processed through the milling chamber and then bring it back out. And if you're using, for example, a basket mill, it would be very challenging for the basket mill to basically suck the mill base into the basket and then bring it back up around it. So we want to keep the viscosity on the lower end. So here I would say the sweet spot is probably 1,000 to 5,000 centipoise. In that range, of course, we can work with much higher viscosities as long as the material is flowing, but we also want to see a donut effect, that visual cue that we get when we are in that optimum viscosity window. So just a few points here. So remember that we are really trying just to reduce particle size by breaking up these van der Waals forces and not really destroying our particles. There's some opinions out there that, or thoughts that if you are milling, the beads will actually crush your pigment particles, but that's actually not really what we're trying to do here. We're just really trying just to, increase the shear by using media, and that shear will allow us to basically separate these pigment particles. Destroying them or crushing them between two beads it does happen, but it's actually pretty improbable because it's almost like if you remember when you were a little kid in a bathtub and you were playing with the rubber duck and you were trying to, catch the rubber duck in between your two hands. What happens is that rubber duck would always try to get away. And it's kind of like what's happening inside of a media mill. So as these beads collide together, we're actually pushing these pigment particles away and through the fluid dynamics. And that pushing motion is actually, it's the shear force that's created by the beads. And that's what's causing the breakup of the binding forces. So it's very unlikely that two beads will actually catch or catch a pigment particle right in the middle where it gets crushed. So most likely it just gets pushed out of the way. But because we have a lot of beads, of course, there is a possibility that some pigments may get crushed, but it's actually very unlikely. And then again, we have these agglomerates. That's the larger clusters. We turn them into aggregates, and then the aggregates, with the help of media, we bring them down to the primary particle size. And it's really just the shear forces that are responsible for that separation. And then, of course, selecting the right additives is critical, that we keep these particles then in a suspended state so they don't flocculate back together. So that's also very important. Just a quick slide showing you the different types of pigments, with some of them, what they look like under a microscope. Different particle sizes here. And that's what we want to do, is just break up these binding forces. So I really like this slide here because it shows you these different clusters. So on the bottom here, we have these agglomerates, which are these larger clusters. And then we reduce those particles to the aggregate size, smaller clusters. And then finally, by using the media mills, we're actually able to get them down to primary particle size. So we really don't have the ability or the shear just by using a Cowles blade to go from the aggregate level down to the primary particle level. So we really need to use a milling system to get us there, because we just don't have enough shear with the Cowles blade. Illustrated here in this picture is actually the entire dispersion process. So we always start out with the Cowles blade to deagglomerate these larger clusters. We are wetting our particles, and then when we reach about between 10 to 20 microns of particle size, using a dissolver blade, once we reach that point, we then can safely move over to a media mill, where we then really start to grind our pigments down to the primary particle size, and then we want to stabilize those. If we go to the milling system before we actually achieve 10 to 20 microns of particle size, then we have a possibility of clogging our screens or dynamic gap in a mill, and that is not good. So we really want to bring down these agglomerates to the 10 to 20 micron aggregate size before we start the milling process, so we don't have any clogging issues with our mills. Here you can see just kind of like the breakout. So again, it's about 10 microns of particle size. When we start moving over to the bead milling process, probably 10 to 20 microns is usually a rule of thumb. And then with the correct type of bead mill, we are really able to produce very, very small particles in the submicron range. We can go all the way, past 100 nanometers. Is not uncommon for certain specialty coatings, like automotive applications, for example. They are really looking for super small particle size due to the finish that they require. Okay, so the dispersion process is always two steps. So we have our pre-dispersion process first. With the Cowles blade, we use a dispermat or dissolver. What we want to look out for here is a tip speed between 18 to 25 meters per second. That's the optimum pre-dispersion window. We want to be in there to really optimize the process and deagglomerating our particles. When we achieve that process and we are left with our aggregates, 10 to 20 microns of particle sizes, that's when we start the milling, or some people call it grinding or fine dispersion process, where we then use a lower rotor speed. We are looking here about 10 to 16 meters per second to achieve good grinding results. And there we have different options. So we can either use a vertical bead mill, which our system is called an APS. We'll talk about that in a little bit. The popular basket mills or immersion mills, or we can use also the horizontal bead mills. Some of you are probably very familiar with, to get us down to the small primary particle size. But before we go there, we would just want to recapture a few important points for the pre-dispersion process. So it's really critical that we select the correct diameter dispersion plate relative to our container size. And you probably know that there is various sizes of dispersion plates, and there is not one that's correct always for the one type of container. So the graph here on the right side will actually kind of show you kind of the range of dispersion plates that we can use for different viscosities for different container sizes. So let's say I make it easy here, 1000 milliliter container. I can use dispersion plates all the way from 30 millimeter diameter up to 70 millimeter diameter. So if my viscosity is really low, I want to use a smaller blade. If my viscosity is very high, I want to use a larger blade. Allows me to move my product and help with the deagglomeration process. But I would always start somewhere in the middle. So a 50 or 60 would probably be a good choice. If I have my viscosity anywhere between 1,000 to 5,000 centipoise, I should be good to go. Another way to look at this is usually as a rule of thumb, the diameter of my dispersion plate should be about 1/3 of the diameter of my container. That way, I can start the process and I should be able, if I optimize, again, 18 to 25 meters per second, if I dial it incorrectly, with a container fill rate of about 50%, I should be able to see actually a donut forming. And the donut is the visual cue that we get when we look inside of our container. We should see actually the formation of that donut. Some of the equipments that are out there, even at this format, not all models will show you the tip speed on the display. So you have to calculate the tip speed. So that calculation is displayed right here. So you have your diameter of your dispersing blade times pi times the RPM of the dispermat running. And if you want to calculate meters per second, it's important that you divide everything by 60, but you also have to express the dispersion blade diameter in meters. So if you have a 50 millimeter blade, you would express that as 0.05 times 3.14 times the velocity of the RPMs of the dispermat. So if you're running, let's say 5,000 RPMs, then you want to multiply that by 5,000 and divide everything by 60, and that will give you the current tip speed that the machine is running at. So it's important to write that down if you want to calculate your tip speed, and that's very, very important, especially if you also upscale to larger types of equipment, because the formula is always the same. So that's important. And here's a nice photo of a donut. You should see the actual blade exposed. You can see the center of the blade as it's dispersing our mill base. And then if we have an optimum viscosity, we should actually see a really nice donut being formed. So that's kind of the visual cue that tells us we're doing a good job, we're putting in energy, and we are now really in the process of properly deagglomerating our particles, and we're turning them into aggregates. So this is a very, very nice slide here. So from the pre-dispersion perspective, we need to watch out for a few things that are very important. So number one is the duration of a dispersion process. So usually when we pre-disperse anywhere from about 15 to 30 minutes, we want to see a donut effect ideally. The tip speed, again, 18 to 25 meters per second. Geometric consideration, again, the blade diameter, as well as the container. So that ratio should be correct. And then, of course, there's different types of cowls blades or impeller discs. So we want to pick the correct one for the type of viscosity we have. 50% fill ratio is what we recommend. You can go as high as 70% and as low as 40%. But if you're milling with a basket mill, and remember the basket mill, the mill head has quite a lot of weight and space. So if I'm putting that in the container when I have 70% fill rate, I have a good chance of pushing my mill base almost to the top of my container, and there is a chance that I might have some spilling. So if I know I'm going to mill with that mill base, I like to stay around 50% fill rate. Pigment filler concentration, of course, is formulation related. That's always very critical. When we are milling or dispersing, temperature is always an issue. We are putting in a lot of energy. So we need to watch out how do we cool our mill base. So it's always recommended, even during the pre-dispersion process, that we already start out with a jacketed vessel, like a double wall container, that allows us to properly cool our mill base while we are pre-dispersing and milling. Of course, when we are milling, we're going to put in a lot more energy, so it becomes very critical that we have that type of jacketed vessel. And also, ideally, we want to also be able to cool our mill head. So basket mills or even horizontal mills or our IPS system have also cooling jackets that allow us to really control the temperature and keep it in a manageable range, so not to overheat our mill base. So that's very, very important. And then again, additives, can't stress that enough, are always important. There's a lot of different types out there. So maybe if you have any issues, you ask Big for a sample, and then maybe you can try and see how those work out for you. And then once we reach the 10 to 20 micron particle sizes, that's when we actually will now start the milling process. So here are some of the key differences. So just using a cow's blade or dissolver by itself, we're gonna deagglomerate, but we have only a certain amount of energy that we can put in. So we are limited by the amount of shear forces there. So it's really only used to deagglomerate and not anything else. And we are not breaking down our aggregates to the primary particle size because we do not have enough shear. But it is a critical step for the entire dispersion process. So you always need to start first using a cow's blade before you move over to a media mill. Again, if the particle sizes are too big, you're going to have a problem with clogging your mill. So you want to start out as small as possible before you start the milling process. And then again, remember that earlier slide where on the drawdown on the grind gauge, you could see the poor color strength on the left. And then when we milled it, everything looked much better. So it's a great example of why we need to do the milling. When we use a media mill, we can put in a lot more energy. So cooling becomes very critical there. Again, we need to make sure we have a good chiller and good cooling capability. And that will give us the ability then to really break down these binding forces and reduce our particles to the primary particle size down into the nanometer range if we want to do so. And that will give us the best performing and best looking product, and also help us by saving costs by reducing the amount of pigments we put in our formulation. So that brings us to the next slide, and we want to talk a little bit about what actually goes on during the milling process. What happens inside of our milling chamber? So we have the impact of our beads, and you can see right there on that slide, we actually, like these beads colliding, again, remember that rubber duck syndrome, we're actually pushing away our particle cluster, and that actually creates creating the shear that helps us to break up these van der Waals forces. So that continuous motion is actually responsible for the reduction in particle size. And it's not like destroying the pigment as some people erroneously believe. So it's really just breaking up of the binding forces. And then, of course, we are also wetting and stabilization, and getting to the primary particles is what size is actually what's happening inside of our mill. We need to talk also about the different types of media. So there is a lot of media suppliers out there. You find that there is steel beads, there is glass beads. There's, of course, zirconium with ceramic beads. And we really want to look at the difference here on this picture, glass, because a lot of people are still using glass versus the advantages that you will get when you upgrade to a heavier and stronger zirconium oxide ceramic bead. You can see that, for example, the specific gravity is much higher on a ceramic bead than on a glass bead. So there's already more kinetic energy that's going to be produced just because we have a higher weight of our bead. So that's what we're looking for. When we are milling, we want to have a relatively high kinetic energy. The hardness is also very critical. When we compare glass to a zirconium oxide bead, we're almost 3 times harder on the nickel hardness using a zirconium oxide bead versus glass. So when I use glass beads, then what happens there is over time, as these beads impact, the glass beads, they will end up sharding. So you're going to have contamination in your mill base. They wear very unevenly since they're not as hard. So then you will have an issue with breakage, you will have contamination in your mill base, and you're going to have uneven beads, which will also result into uneven milling results, uneven milling performance. In some cases, your milling time will be extended. In some cases, it'll be reduced because you don't always know the state of your glass beads. So here at BIC, we highly recommend to stay away from glass and use the more expensive but much better performing ceramic beads. And you will be very glad that you did so, because you will see that you have much more consistent results from batch to batch. And you will also see that you're probably milling down a little bit faster because your kinetic energy is much higher. And then you won't have any cross-contamination issues because you will not end up with sharding inside of your mill base. So it's very important to evaluate, what type of beads you're using. And then, of course, ceramic beads were much better. But even then, it's important that you screen those beads after your milling process every so often, and you use maybe a mesh screen to basically sieve out the fines and ensure that only the really round beads stay behind. You will find also that some of the suppliers on the market will offer lower cost ceramic beads, but actually we have seen that as well. If you look at that under a microscope, some of these beads are not spherical, so they actually look more like a football. And that's also something you don't want. You want to have very round spherical beads. Spend a little bit more money, and you want to stay away from ceramic beads that are not spherical and that are more in oval shape, because they also will wear very unevenly, and that will also give you inconsistent milling results. So it's really critical that you watch out for those factors. There is, of course, different sizes available. They work also without dispersion, so it's important. So if you change bead size, to always remember that you have to then also change the screen size or the dynamic gap. So when we mill, usually in our basket mills, we have a standard 0.5 millimeter mesh, and then we can use 1 to 1.2 millimeter size media. So that's very important. And as if I'm going down in media size, I will also have to change out my screen and make the screen smaller. Okay, so this is a really good slide, kind of showing you the influence of the bead weight. So let's say I'm using, the glass bead and I have relatively light beads. It's like trying to hammer in that nail in a board with a very small hammer. So it'll take me many, many impacts, if I use a small hammer. I may never even be able to drive the nail into the board if my hammer is too small or too light. So if I'm increasing the weight of my hammer, kind of like the beads, then I will need less blows, and therefore my nail will be driven into the board much faster. Of course, if I use a very heavy one, my kinetic energy is much higher, and maybe I can do that with only one impact. So it's very critical to watch out for the type of bead and that you have relatively high weight or specific gravity with your beads that will help you reduce the milling time. Here's just a calculation of the kinetic energy. I just always want to show kind of that slide. So if you want to write it down, or we are actually recording that presentation so you can kind of, come back to that if you're interested in figuring out, how to calculate the kinetic energy. So in this slide here, we're actually looking at some of the pigment particles clusters right in the middle of our picture, and then the beads as they are actually touching each other, and right in the corner where you can see kind of the triangle, this is actually where all the shearing motion or action happens. So as the beads collide together, and this is all in a suspended state, of course, in liquid, now there is all this shear force that's being created, and that's actually causing these particles to break up. So it's not that we are actually crushing the pigment in the middle between the beads. Remember the rubber duck, it tries to get away, and that's what's causing the breakup of these van der Waals forces. So that's really what's going on inside of our mill. We're doing the process of milling. So we want to talk a little bit about the different critical parameters during the milling process. So particle size after the pre-dispersion process, again, 10 to 20 microns is kind of a rule of thumb. This is what we need before we start the bead milling process. Bead size and weight, we talked about that. That's very critical. The bead type, again, try to stay with ceramic and not glass. We didn't touch on steel beads. They are very heavy, but they have one problem. Steel beads, even though they have a relatively high specific gravity, they are contaminants. And what that means is if you're milling and these beads collide, because they're stainless steel, let's say you're trying to mill a white slurry, you will end up cross-contaminating your slurry with residue from the stainless steel, from the metal. And that will actually cause discoloration of your mill base. So if you have a beautiful white, that can turn into a gray slurry relatively quickly if you're using steel beads. Also, if the mill itself is outfitted with stainless steel components like a stainless steel rotor or a stainless steel milling chamber, and you're trying to mill, white pigment, TiO2, you're going to have issues. So you might also want to look at, outfitting the mill with ceramic components. So there are zirconium oxide lined milling chambers. There are zirconium oxide milling discs or rotors that will help with that. And that's very important because you do not want to have discoloration of your mill base, especially when you're running very light or white colors. If you're doing blacks or dark blues or anything like that, or browns, then it's not really an issue. You can't really detect that. But if you're doing a lot of white colors, highly recommended that you use ceramic. Bead volume, of course, depends on the type of mill we are using. Using a basket mill, using a vertical bead mill, which has a much higher bead loading, or a horizontal medium mill. So each mill has their own specifications. So there is not one set, or one rule that you always need to use a certain amount of beads. It depends on the milling chamber size and, of course, the type of mill that you're using. So that would be in the operator's manual. You can actually usually see a table that details exactly the fill rate of the milling chamber with beads. Again, shape of the beads, very critical. You want to try to get them as spherical as possible and not save costs by buying some, inexpensive brand that when you look at it under the microscope, they more look like footballs. You don't really want that because that will give you very poor milling results. And then again, I always mention it numerous times because it's so important. The tip speed when we're milling should be between 10 to 16 meters per second. We didn't come up with that number. So that's kind of an industry standard used by almost anybody that's doing milling based on experience and performance. So this is really the optimum milling tip speed window that we recommend. Product temperature, again, when we are milling, we're going to put in a lot of energy. So we really have to maintain lower temperatures. So you need a good powered chiller. And when you select the chiller to work with your mill, you should always get the power of the chiller to match the power output of your mill. So if you, let's say, have a 1.5 kilowatt dispermat, then you want at least to have 1.5 kilowatt on your chiller. Okay, if you go lower than that, then you're going to eventually heat up the material and the chiller will no longer be effective enough to really continue cooling the material, and then you'll have to shut down and it's a pain in the butt. So don't save, always get a very at least comparable chiller to the motor power of the dissolver. So that's very important. Energy input, the more energy we're putting in, the faster our milling process and the better the results. And of course, energy input means also rapidly increase our temperature. So again, chilling, extremely critical when we are milling. The number of passes. So when we have a horizontal mill, that means how often does my mill or my mill base travel through the milling chamber, come back around. Or when we have a basket mill, how often does my mill base go in and out of the basket? So that's critical. The milling time. So there is not really a number we can put on that. So it's really product and volume dependent. And also, of course, what is my final particle size or particle size distribution? The smaller I want to go, the more milling time I need to add. So we have, for example, some products, that we milled with a basket mill in, 45 minutes, and we were able to get to about a 2 or a 1 on a Hegman. And then when we use a horizontal mill, that would also take about the same amount of time. But we have seen where these numbers go up rapidly depending on the product. So it depends really on the type of material that you're trying to mill. Viscosity of the mill base. Again, we want to have flowable product. We want to try as low on the viscosity side as possible. But if we are, let's say, too low, that's also not good because that makes it more challenging to put in energy. So we want to have, again, between 1,000 and 5,000, kind of the sweet spot. Of course, we can have higher viscosity. That's okay as long as the material properly flows. Milling tool diameter, again, just like that, what we had with the dispersion blade. A milling tool diameter also plays an important role, especially when we want to calculate for upscale. We want to also look at that as well. The type of material of our rotor, again, ceramic, if you want to have color stability. If it doesn't matter, you can use stainless steel because discoloration or bleeding of the steel might not be noticeable when we're running very dark colors. And then, of course, some people prefer vertical bead mills, some people like horizontal. So it really depends on your preference. But we'll talk about the different milling systems here in a moment. I mentioned earlier the modularity of our dispermat. So here is an example of a dispermat in the middle. It's a dissolver, but on top, right below the motor, we have a clamping ring. that we can remove. It's like a bayonet style, and that allows us to remove the dissolver shaft and replace it with any other accessory. We have a rotor stator accessory. We have the APS, that vertical bead mill accessory. We have a basket mill accessory that will fit right on there, or even a vacuum system, because some people prefer to disperse or mill under vacuum to remove any type of air or foaming issues. And then on the bottom, we have a wall scraper that is also an accessory that will work with our disper mat. So that makes a unit very versatile and cost effective, because you need only one machine to do all the different steps rather than buying multiple pieces of equipment, clogging up bench space and so on, more maintenance costs. This way I buy one machine and I can buy all these cool different attachments depending on what I want to do. And you don't need to buy them up front. You can buy them as you need them. Some people might just want to start out with the dissolver. They may not need a milling system up front, and then they can just buy one at a later time. Closer picture here is a disper mat right here with the beautiful C controller that gives you all the critical values for upscale, especially when you are milling. The small laboratory scale units can go up to about 20,000 RPM. We offer them also in explosion proof. And then we have software that allows you to track all your data, store the data, send it over to a computer in an Excel sheet. And that also is all available, that modularity and design from lab scale pilot, as well as for our manufacturing grade units. So the different accessories allow you then to use the disper mats as a homogenizing tool. So you could, add a propeller or a butterfly tool. We can use them as an emulsifier with that rotor stator, or as a disperser by using the cowls blade and then moving over to a milling system, the basket mill or that vertical bead mill. And that brings us to the very first milling system we're going to talk about today, which is our tourist mill TML, the basket mill. And that basically allows us to really do a good job bringing down our aggregates down to the primary particle size. You can see the picture on the bottom right there is kind of a snapshot of basket mill, what's inside. So inside of our basket mill, we actually have on top, we have a pumping and steering system, which is kind of a wheel with some edges on top that will actually create a vortex. And that vortex will actually suck our mill base into the basket. What you don't see in this picture, of course, is the media that's somewhere in between right here around the pumping and steering wheel and above the milling disc, which is right below. And on the bottom of our milling disc, we actually have a screen. And then right outside of a screen is a cowls blade that will have the purpose of actually helping us to draw the mill base out of our basket and then push it back around to the top, where then that vortex wheel takes over and sucks it back in. So we have a very good circulation of our mill base in and out of the basket, and that is very important. The second very important feature is the cooling ability. As you can see here, we actually have cooling lines that go through our milling chamber wall. And that is very important that we're cooling right there, because this is where we're going to put in all the energy, and that's where you're going to have the biggest problem with increased heat. So this is where we need to cool. And some basket mills or immersion mills actually have a screen on the side right here, and also a screen on the bottom, but the screen on the side has an issue. And the problem there is that it will wear down very quickly, because that's where all of our media gets basically thrown all over the place when we are milling at very, very high velocity. So the beads will actually impact the screen on the side wall of the basket mill. So and you can't cool it then either, because you have a screen right there. So we purposely design a basket mill without a side screen and have only a screen on the bottom to improve cooling and reduce wear on the basket. And that's really important and effective. And we found out that the cowl's blade on the bottom of our screen, right outside the basket mount, does a really good job moving the mill base out of the basket and then pushing it back to the top. So we do not need a screen on the side wall, and we don't want a screen on the side wall for the reasons I just mentioned. And then we have different size screens, of course. So the standard screen is a 0.5 mesh, and we can go down all the way to, actually we offer a screen 0.1 millimeter mesh. So that actually 0.2, it's an old mention there. We actually have one now that is even smaller, allowing you to use 0.2 or 0.3 millimeter media. So here is a good graph kind of showing you what happens here when we use a basket mill, pump it back around, up and down. And then you can actually, in the illustration, you can actually see the beads right in here on the left side. And the right side, this is when we move out the basket out of the slurry. This should be our milled material. Okay, that's a picture of a larger scale basket mill. So we have that screw right there. That's for bead filling. We remove that screw, we put a funnel in, and then we can add our beads that way. On the smaller size TMLs, we can add the beads right in the middle through the center hole where we, where the mill base goes in. We make basket mills for very small quantities, like a quarter liter, like a quarter quart, all the way up to 2,000 liters of product. And I can report to you that we have done some tests. We have excellent upscale results from our lab scale to manufacturing, almost one-to-one, which is very important. Very easy to clean a basket mill. So that's another big benefit. And you don't have really hardly any wear. There are no seals, O-rings, or anything of that nature. So it's relatively easy to maintain, relatively cost-effective compared to a horizontal mill, and does an excellent job. The only issue here is that you are going to be limited to a particle size of about 500 nanometers. If you want to stay within an efficient milling time. You can continue milling, it gets a little bit smaller, but it will take you a really long time. So if you want to go smaller than 500 nanometers, then a horizontal mill would probably be a better option here for you. Here is an example of two large manufacturing scale TMs. They were installed in St. Louis. And you can see that the blade is not installed yet, but the basket is on them already. So this is actually a revolutionary 2-in-1 system. So we actually have a production scale dispermat that acts as a disperser. And with the push of a button, I can then lower my basket, and now this whole thing becomes a milling system. So I'm very effective. I don't have to push containers around from one mill or from a disperser to a mill. Everything can be done on one machine very effectively, and it's a great design. Then we have also the APS system I mentioned earlier. It's a vertical bead mill. This is available for our laboratory scale models. You have two containers. You have a top container. You can do your pre-dispersing in there by just using a cowl's blade. When you're done with your pre-dispersing, you swap out the blade for a milling disc. Here in this picture, you see a double milling disc. And then you basically push and you add your beads. You can add 100% bead loading. So if I have, let's say, 500 milliliter of slurry, I can add 500 milliliters of beads, which is really good. I have a lot of beads then in my container, helping us with the, breakup of our particle binding forces. And then when I'm completed with the milling process, I didn't mention that there is also a cover that you have to put on during the milling process. There's a clamping ring that goes around it to secure the cover. So we don't want to have product flying out of the container while we are milling. But once we complete the milling process, we can open up a drain plug on the bottom of our top vessel. There's a screen embedded in there. And then we hook up an air hose. You can see on the right picture, there is a socket. That's where we actually hook up our air hose. and then we can purge our mill base out of the container with air pressure into the container right below. And that actually is a very beautiful, effective way, a quick way of milling relatively small volumes. And in the only drawback here is that it's not really scalable to manufacturing due to the large volume of beads that are required to run an APS system. Can you imagine if you have a 1,000 liter container, you'd have 500 kilo of beads? It'd be very difficult to handle, but also very, expensive, if you have that many beads. That kind of is a graph showing you kind of the layout of the APS system. You can see that drain plug on the bottom on the left picture graph right there. You can see there's a lot of beads inside of our slurry, helping us with having really good milling action. On the right side, you can see the air hose plugged in and the draining through air pressure of our mill base into the container right below after we remove the drain plug. And when I'm cleaning, I just put the drain plug back in place. I put a cleaning agent into my container and I run it for a few minutes, and then I purge it out exactly the same way as I will purge out my mill base, and that would help me clean my APS system. And I rinse, repeat until it's very clean. And that is a very easy way, effective way of milling, and also cleaning is very simple. Here's a more of a close-up of the APS system, but a beautiful way of milling small volumes. Then we have, of course, the horizontal medium mills. On the left, you can see our lab scale, the SL, and then we have the RS for production. We also offer nano versions that allow you to mill down to under 100 nanometers very effectively with our horizontal milling systems. So there you can either do a pass or recirculation mode. They have an integrated pump and steering system to actually help you put the material into your milling system. So they can go up to 6,000 RPM. We can independently regulate the rotor and the pump speed. And there are different materials available. Again, you would have cross-contamination issues if you wanted to produce a white mill base and you use stainless steel. So recommend use ceramic or anything of that nature, or very abrasive materials. You can also use hard metal. We have large choice of different media size for the standard configuration. And on the nano version, we can go also down to 0.1 millimeters and up to 0.3 with the nano kit. And you can buy a nano kit separately and implement that with the standard SL, turning normal normal horizontal mill into a nano mill. Very, very nice feature. So then I know we are kind of short on time, so I'm going to just browse through this quickly. We have different control capabilities for quality and safety. So we can also program what are called cutoff values or cutout values. These are limit switches for our temperature range. For example, if we don't want to exceed a certain temperature limit, 80 C, then we can program it and we can teach the machine to stop at 70 or 75, and we can get warnings also programmed in that will alert us that we're approaching the temperature limit, and then the machine will either power off or run with a different speed. We can also store our parameters. We can create a batch file and program all the cutoff values, all the other values like our energy input or our speed, and then milling tool diameter and so on, and or even height in our vessel, and then we can replicate that the next time when we are running the same material, helping us, to maintain product consistency. We can do a net power calibration, allowing us to really set all the energy input and torque values to a 0 point without the influence of products. So when you turn a machine, you can run it it will automatically run for about 60 seconds without product, and then it'll set all these values to a 0 point, that when you're actually dispersing or milling, the power input and torque value will only be reflective of your product and not with any machine input. Here is a picture of our lab in Germany. If you're ever over there and you want to visit, you're more than welcome. We can also do trial work over there for you if you have a sister company or another facility over there that wants to come in and review the equipment. Always welcome. And then we also have a lab in Connecticut that's actually, we're going to insert here a new picture very soon. But we have a lot of other equipment that is in there, but we can do all the same things they can do in Germany. We have a horizontal mill. We have new AE units in there. We're also going to get a new CV3 Evo, smaller lab bench unit. We have all the different attachments, the basket mills and rotor stator and vertical bead mill vacuum system. So if you ever want to come in, feel free, let us know. We'd love to have you run experiments with your product and show you the value of our systems. These are the new machines that we have now in Wallingford. And they're really cool. So the laboratory in Wallingford is a first-class lab facility. We're able to upscale to large equipment. We have the ability to leverage the synergies between our instrument and additive business. So if you come in and you have, let's say, formulation questions, or you want to try different additives, when you want to explore the basket mill, for example, then we have a chemist working with us and you to help us make improvements. You can also come in just to review the equipment without running a trial. And then we can also help there if you want to come in to learn more about the technology and a presentation, bring in a team, we can also make that possible. With that, I want to appreciate your patience. Thank you for coming today. And I'm opening up to questions. I know we are late on time.
Yeah, thank you so much. Yeah, if anyone has any questions, just jot it down real quick here in the chat function. Otherwise, like I said, you'll receive an automated email with a link to this recording. If you have questions later today or later in the week, next week, just hit reply and we'll route it to the appropriate media milling and dispersion experts. So thank you, Andy. Doesn't look like anyone has any questions here. Thanks for motoring along there. I was watching the slides. I'm like, oh, is he going to make it? So we appreciate you, Andy, your expertise, knowledge, spending some time with us. So thank you very much. And we look forward to seeing you on a future BitGardener web seminar. Thank you.
Thanks, everybody. Really grateful that you joined us today. Thank you.